Okay guys, I have another video here for you. This one deals with the second and third laws of thermodynamics. So we're going to go through those, and we're also going to learn how to calculate entropy changes for both phase transitions and chemical reactions. So this is a statement of the second law of thermodynamics. It states that spontaneous changes cause an increase in the total entropy. That is the entropy of both the system and its surroundings. And so I've outlined that here. Delta S is the total entropy change for the process, which has two parts, a part coming from the system and then a part coming from the surroundings. The sum of these must both increase for a spontaneous process. And this allows us to distinguish between spontaneous processes and non-spontaneous processes. So for a spontaneous reaction, delta S total will be greater than 0. For a non-spontaneous process, delta S will be negative. This bullet point here summarizes both the first and second laws of thermodynamics. The first law, in its short statement, tells us that energy cannot be created or destroyed. This is called the law of conservation of energy. And for the second law, the short statement is entropy is always created. So delta S total is used as our criterion to determine spontaneity. And for constant temperature processes where you have a large surroundings, you can calculate delta S total as delta S for the system plus this term for the surroundings. And if you use the fact that heat gained or lost by the surroundings is minus that of the system, then you get this expression here. Now, we will use this in one of the example problems in a second. However, it's not so critical for the exam. However, these conceptual points are very important, so be sure to review those. In this slide, what we're going to do is learn how to calculate the delta S for a phase transition. So that's what this TRS stands for, a phase transition of some sort. It's calculated as the heat involved in the phase transition divided by the temperature change. And for constant pressure phase transitions, most of them are, the heat is equal to the enthalpy change of the phase transition. So to calculate the delta S for a phase transition, you need to know the enthalpy change for the phase transition, and you divide it by the temperature at which the phase transition occurs. What I've listed here are different phase transitions. The first three phase transitions that I have here are endothermic phase transitions, where you are going from a more condensed phase to a less condensed phase. These are endothermic because in order to go from a solid to a liquid, you need to break intermolecular bonds. That is, you need to free up the molecules so that they can move around. The same thing is true in going from a liquid to a gas or in going from a solid to a gas. I did want to point out that for the melting process, the term fusion is a synonym for melting. That might be counterintuitive. You might think that fusion would be going from the liquid to the solid, but that's not the case. The term fusion means going from the solid state to the liquid state. And as I was saying before, each of these different phase transitions has a positive enthalpy change. And so when you plug that positive enthalpy change into the phase transition formula for calculating the entropy change, you are going to wind up with a positive delta S. So as you go from a more condensed phase to a less condensed phase, it is accompanied by an increase in the entropy of the system. For the opposite of these, so the opposite of melting is freezing, the opposite of boiling is condensation, the opposite of sublimation is deposition. When you go from a less condensed phase to a more condensed phase, you change the sign of the enthalpy, and you wind up with a negative enthalpy change for each of these phase transitions. So when you plug in a negative value for delta H, you're going to wind up with a decreasing entropy. This problem illustrates the entropy calculation for a phase transition. We're looking at the melting of ice, or the fusion of ice into liquid water. It's accompanied by a 6 kilojoules of heat for every mole of water involved in this phase transition. and we are being asked to calculate the entropy change for the process. So we need to know this formula. This is how you calculate the entropy change for a phase transition. You take the 6 kilojoules per mole of heat and you convert it to joules per mole, and then you divide by the phase transition temperature in units of Kelvin. And so in this case, you get 22 joules per mole per Kelvin. And I wanted to point out that commonly enthalpies are expressed in kilojoules, whereas entropies are almost always expressed in joules. And so there's usually a factor of 1,000 that needs to be applied in order to convert delta H into delta S. In the follow-up problem, we're being asked to comment on whether or not this process will be spontaneous at minus 10 degrees Celsius, and will it be spontaneous at 10 degrees Celsius. Just use your intuition and you'd know the answer, right? If you had ice at minus 10 degrees Celsius, for example, in the deep freeze, it's not going to spontaneously turn into a liquid, right? It's too cold. You need to get it above the melting point in order for ice to melt. Conversely, if you did have ice at 10 degrees Celsius, it would spontaneously melt to form liquid water. The calculations for that are illustrated here. In order to determine whether or not a process is spontaneous, you have to look at delta S total. Okay, it's not sufficient just to look at the delta S for the system. You need to look at both the system and what happens in the surroundings. And for phase transitions, you would use this formula, delta S minus the heat divided by the temperature. If you plug in the heat, 6 joules per mole, and then you plug in minus 10 degrees in units of Kelvin, what you're going to find, as you would expect, delta S total is negative, which means that it's a non-spontaneous process. If you plug in the temperature of plus 10 degrees Celsius in units of Kelvin, you are going to get a positive delta S, indicating that it is a spontaneous process. As I said earlier, you're not really going to need to use these equations on the exam. However, you do need to be able to calculate the delta S for the system involving a phase transition. So be sure that you can do these types of calculations. This slide introduces the third law of thermodynamics. I'll just go ahead and read it. A perfect crystal at 0 degrees Kelvin has an entropy of 0. And so let's think about what's going on here. A perfect crystal would be a substance where every molecule in the crystal is in its lattice position. So there's no defects in the lattice. It extends outward forever, essentially. And when it's at 0 Kelvin, none of the molecules are moving, right? There's no thermal energy present in the system at 0 Kelvin, and so all of the molecules are fixed in place. There's only one way to rearrange the molecules in a perfect crystal at 0 Kelvin so that there's only one microstate available to the system. If you use the microscopic definition of entropy to calculate the entropy, you'd plug in 1 for W. Natural log of 1 is 0, so the entropy of the perfect crystal at 0 Kelvin is just 0. Now, if you increase the temperature of that crystal, the molecules are going to start moving again, and the entropy is going to go up. The utility of the third law is that it allows us to calculate entropy changes. Okay, and so we will be working with what are known as the standard absolute entropy values, which are represented by this S circle. And we're going to be using those values, which you can look up in thermodynamic tables, to calculate the entropy change for a chemical reaction. And that's outlined here on this slide. We follow that same products minus reactants approach that we learned about in the thermodynamics review, right? So in there, we were looking at calculating delta H for a reaction. We would look up enthalpies of formation in our thermodynamic tables, and then use an equation like this to calculate the enthalpy change for the reaction. Here, we're calculating the entropy change for the reaction under standard state conditions, and we look up the absolute entropies for each of the products and each of the reactants. We multiply the products by their stoichiometric coefficients, add all those together. We multiply the reactants by their stoichiometric coefficients in the reaction, and then subtract those from the products. and that gives us the delta S value that we want. As we looked at in the previous video, you can actually estimate the sign of delta S without doing a calculation, but then you use this equation to calculate the actual value of delta S. And so here's an example. Again, this is a phase transition, and we're just going to illustrate using the products minus reactants approach for this phase transition. So here we've got water vapor. It is being condensed into a liquid. We expect the sign to be negative because the number of moles of gas decreases. In order to calculate delta S, what we'll do is we'll look up the absolute entropy values in the thermodynamic table. For water vapor, the value is 188 joules per mole per Kelvin. For liquid water, it's a smaller value, as we would expect, 70 joules per mole per Kelvin. In order to calculate delta S, we'll take the absolute entropy of the product minus the absolute entropy of the reactant, and that gives us this minus 118.8 joules per mole per Kelvin. Here's an actual chemical reaction. We've got hydrogen reacting with ethylene to give us ethane. We look up the absolute entropies for each of these species in the thermodynamic table. I've got them listed here. And to calculate delta S, we start with the products. The stoichiometric coefficient is 1, so it's just 1 times the value for the ethane. Then we start subtracting off the reactants minus the absolute entropy of hydrogen gas minus the absolute entropy of ethylene gas. Plug in these numbers, and we get minus 120.6 joules per mole Kelvin. Here we have a more complicated reaction. I've left this as an exercise for you. Don't forget about the stoichiometric coefficients. So you're going to take 2 times the number for carbon dioxide, plus 4 times the number for liquid water, minus 2 times the number for methanol, and minus 3 times the number for oxygen gas. And that'll give you the value. Here's another example for you guys to try on your own. And I'm going to go ahead and stop this video right here.